Hi kiddos, welcome back. We're moving into another phase of calorimetry. We're going to go back to our MCAT formula. And this time I'm going to avoid using delta H because bomb calorimeters, which is what we're doing now, no, we're not dealing with explosions. I know you all want to do explosions. Bring me in gummy bears and we'll burn some gummy bears. That's always a fun one to do. All right, but we do call it a bomb calorimeter because what is done is we ignite a substance in here, fuel, oil, food, whatever substance that we want to know the energy that's involved in the combustion. So calorimetry is a technique. It's the energy or enthalpy. I'm just going to put both. That's not always the same. Enthalpy is the energy at constant pressure. Okay, so we're not going to get too picky about that, but we're looking at the heat change. Now, in a bomb calorimeter, what happens is we combust in this little chamber. We add oxygen, so pure oxygen's added into the chamber, and then the heat from the combustion is released into the water. And so what is actually measured are the temperature changes in the water. And so what we'll be able to equate is that the heat given off by the combustion is going to be equal in magnitude but opposite in sign to the heat absorbed by the water. That's not saying the heat absorbed by the water is negative. It's saying they're equal in magnitude, opposite in sign. Okay, so the heat's going to release, the combustion's going to release heat, so the temperature of the water should increase. Now, in the real world, they also consider the fact that not only does the water absorb heat, but the calorimeter itself can absorb some heat. We are going to ignore any heat absorbed by the calorimeter, and we're going to focus only on the heat absorbed by the water. And that's going to give us a fairly simple MCAT calculation. We'll know the mass of the water, we know the heat capacity of water, and we'll measure the temperature change of the water, and we'll be able to determine the heat that is involved. So let's take a look at this. We're going to take sugar, we're going to combust it, and it gives us the mass of water, and it says, what is the heat change for that amount of sugar? Okay, so Q for the combustion of my sugar is going to be equal and opposite Q for water, and that's going to equal my mass of water, 240 grams, times my heat capacity, specific heat capacity, 4.184 joules per gram degree Celsius. Now you got to get that final and initial in there. 2755 minus 22.53. And so my heat of combustion ends up being that the Q of the water was positive 540, so it's going to be minus 5040 joules. Okay? So the water gained heat, the combustion lost heat. Okay? So this asks for the heat change for the sugar. Let's get some perspective in here. I like to put this type of thing into the context of, I'll say something like a Butterfinger bar. So let's convert this to food calories. I thought this would just be a curious calculation. So that's, not many grams of sugar. We've got 5040 joules. 1 calorie that would be given to you for every 4.184. Now, that's an energy calorie. A food calorie is given a big capital C, and that's 1,000 scientific calories. So a food calorie is a kilocalorie, right? 1 food calorie is really a kilocalorie. But they don't call it that. They just use a big capital C instead. And when we did this, we got 1.20 calories. Okay, that's barely a lick on a Butterfinger bar. Okay, it's just not much. Okay, now what if we were asked to determine on a per mole basis? Because if we put it on a per mole basis, we can publish that value, and it's a better comparison than having to say it's per 0.303 grams. We want it either on a per gram or a per mole basis, and so we would take 0.303 grams times 1 mole per 342.22 grams. That gives us our moles, 8.85 times 10 to the minus 4th moles. And if it had asked us to do it on a per gram basis, I would have just divided by grams. But since it asked on a per mole basis, we're going to take that minus 0.5040. Okay, there might be a typo here because one of mine says 49, so let's double check that number there. Okay, and I'm going to divide it 8.85 times 10 to the minus 4th. It says 5049 in one place and 5040 in another. My key does. So let's check that number, okay? And that is moles. And this was joules. And then we want to convert that joules to kilojoules. You know how to do that. I'm not going to waste your time on that. Minus 5.70 times 10 to the 3 kilojoules per mole. Now the next one says, would it be a product or reactant? It's a product because heat's released in a combustion. I can't even spell. It's too late at night. It's released in a combustion. In other words, it's exothermic. So we would write it as a product. Okay, let's do one more quick one of these just to reinforce it. I'll do it a little quickly, so you might want to slow it down and rewind and or ask me questions in class. Okay, but for those of you who are getting it, I also don't want to belabor it by doing too many. So I've got 2 more examples here. Okay, I'm going to just do the rocket fuel example, and let me give you the answer for this one. So this one turns out to be, should be minus 41170 joules for the 1 gram, and it's minus 4288 kilojoules for 1 mole. Okay, so jot those answers down, and I'm going to just do the hydrazine one. I don't know why, mainly because I think rocket fuel's more fun than octane. That's no other reason than that. Hey, something's burning, way cool. Okay, so we've got a 1 gram sample of hydrazine, and so we want to know the change in heat. So Q for my combustion of my hydrazine is going to be equal in magnitude but opposite in sign, Q for my water. So that's going to be the opposite in sign. Now my mass of water is 1,500 grams. Make sure that's in grams to match your heat capacity. Times 4.184 joules. That's going to give me my answer in joules. We always do final minus initial. So it's 27.79 minus 24.62. And so I would get minus 1.989 times 10 to the 4th joules. For the molar or per mole, let me show you another way to do this. I have 1.989 times 10 to the 4th joules. All you have to do is convert mass to moles and divide joules by moles. It's really all you have to do. That's per 1 gram of hydrazine, right? Some of you are going to like this way better. I'm going to multiply that by 32.06 grams of hydrazine, so I get grams to cancel, per 1 mole. That's another way to do that. Or you can just convert mass to moles using molar mass. And that would give me my moles. And then take your joules and divide by your moles. Just do it in 2 steps if you don't like this way. And then I want to get rid of my kilojoules. Or excuse me, I want to get rid of my joules and go to kilojoules. 1 times 10 to the third to 1. And we get 637.7 kilojoules per mole. And we did it in just over 10 minutes. Okay, we'll be working on these in class. Until then, this is signing off.